when you can't go outside, that just becomes that much harder. And like my aunt and uncle had to evacuate. Luckily they're fine and they've been able to go home. But the reason I'm saying this is because I want y'all to know that mental health is important and that should be a priority. So if there's anything that I can do to make things less stressful for you, please feel free to let me know. I want to teach you about galaxies, so that's what I'm going to do. But I also understand that this is not a great time to be living in the Pacific Northwest. Or America or the world. So I'm just want to acknowledge that because it seems hard to not acknowledge that. And I cannot tell you who to vote for, but I can tell you to vote. So that's gonna be, there's still time to register if you haven't yet. Whitman has a policy about politics, so I have to be semi-careful, but we are allowed to tell students to vote. So that's all I'm gonna say on that. But yeah, please do, if you're feeling stressed, if there's a day you can't make it to class, whatever else, that is fine. I always post these online after, and the material is all there. It doesn't need to be done. I think the only thing that has a due date is the photometry project right now. So things will be available. There's no late points for the in-class work. Okay. It's like most people have signed on, so I'm gonna go ahead and get started, but does anyone have any questions about anything points-wise, late work-wise, anything they want to add before we get started or ask? Okay. Okay, so this is where we left off last class. We talked about how to measure star formation, and I wanted to just end that kind of conversation with a little bit of discussion about some of the other laws of star formation that we talk about. So the first one is something called the Kennecott-Schmidt, or the KS relation. Just so you guys know, a little bit of kind of weird nomenclature stuff. Some people call this Schmidt-Kennecott. Some people just call it Schmidt. There's a little bit like the kind of rule is Rob Kennecott calls it the Schmidt relation. People who work with Rob Kennecott call it Kennecott-Schmidt. And then people who don't work with Rob Kennecott call it Schmidt-Kennecott. But so if you hear people talking about KS, Schmidt-Kennecott, or Kennecott-Schmidt, or just Schmidt, they're probably all referring to the same thing. Rob is one of my co-authors, so I call it Kennecott-Schmidt. The idea, it was one of the first laws kind of realized about star formation. It got proposed in the 80s, and it's this idea that there should be a relationship between the surface density of gas and the surface density of star formation within a galaxy. So that's what we're seeing here. There's a nice linear trend where we have the surface density of gas. So sigma is always going to be a surface density or a surface brightness. Yeah, so that just means that we're taking the values we have and dividing them by area. We usually do a surface density in galaxies or a surface brightness because we can't know volumes because we're looking at two-dimensional images. So we have instead of a volume density, we're often looking at an area density or a surface density. So surface density of gas, hydrogen gas, versus a surface density of star formation rate, so in solar masses per year per kiloparsec squared. And we can see that there's a nice trend between the amount of gas and the density of that gas and star formation rates. So this is kind of what you would expect. If there's more stuff to form stars, there's more stars forming. But it also shows you, it's also a measurement of the efficiency of star formation within a galaxy. So these different lines here show the efficiency in which a galaxy is turning its gas into stars. If we turned all of our gas into stars, we would be at 100% efficiency. If we were turning 10% of our gas into stars, we're at 10%, and then 1%, and so on. there are some weird starburst galaxies that seem to be at or above 100%. They probably aren't, but that's either a mistake in a measurement somewhere or something else weird going on. So those above 100%, you know something's off, but starbursting galaxies do get to be pretty efficient at forming their stars out of gas. We can also see that at lower gas masses, there's a turnover. So there's this kind of knee here. And what this tells us is that there's a certain density where you just don't have enough gas to form stars. So if you look at a galaxy and you look at the gas mass, at some point, you need a certain threshold density to form stars at all. And if you don't have that threshold density, there's no star formation. So this is another plot that gets made in a lot of extragalactic astronomy papers. We'll see a Koenig-Schmidt plot, a KS plot. So it's something that if you do go into this, there's a good chance you will make this plot eventually out of your own data. The other kind of star forming law that I wanted to talk about is what we call the star formation main sequence. So sometimes this is also called the galaxy main sequence. Not quite as nice as the star's main sequence. It's a bit fuzzier. It's related to what you guys did when you made your color magnitude diagram, but instead of color magnitude, we're looking at a stellar mass versus a star formation rate. So star formation rate versus stellar mass. So you can kind of think of stellar mass as magnitude because, sorry, more stars is brighter. So it's kind of magnitude, and then star formation rate is kind of a color because more star formation means bluer. So it's kind of a color magnitude diagram just with some conversions thrown in. And what we can see is that there's a blue sequence of spiral galaxies and a red cloud of elliptical galaxies. So this is our star forming main sequence, similar to the star formation, the CMDs that you made, but with a little extra conversion, and is another plot that gets made quite frequently. The other thing that's kind of interesting that a lot of researchers do is they measure this fit between star formation rate and stellar mass, and they see how it changes throughout time. So the slope of this line changes without redshift. So if we look at galaxies at different redshifts, we can measure how star formation rate per solar mass is changing over time, which is another interesting thing that comes up a lot in research papers. I think this is actually, so the reason why this looks funky is because this is a star formation rate per stellar mass. So it's a little weird. This is a specific star formation rate. So you just take your solar masses per year and then divide that by your total mass. It's a little funky, but I like this plot because it has all of the SDSS data. So those were the two main star forming laws that'll come up if you do more galaxy research. So I just wanted to make sure you had seen those. Does anyone have any questions about those before we switch topics to galaxy structure?
What's the mass on the bottom? Sorry, the x-axis?
Yeah, so that's the stellar mass. So M star is the stellar mass, and then it's in solar masses. So yeah, that's the, it's just the total stellar mass of a galaxy, which is, stellar mass is different than total mass because total mass involves dark matter and dust as well. Good question. Anything else? Okay. So we're gonna switch topics and we're gonna get into a little bit of galaxy structure. So my idea for the next few classes is we're gonna start really big with looking at kind of big structures within galaxies. Next class, we're gonna go really small and look at some of the smaller structures in galaxies. And then we'll use next week to kind of connect those two scales. So today we're talking about bulges, disks, spiral arms, and halos. In the next class, we'll talk about PDRs, H2 regions, and giant molecular clouds, which are in those disks and halos. And then finally, we'll just unite those by having a larger conversation about the ISM or the interstellar medium and what's going on in there. So that's kind of the plan for the next few weeks. this week will be more programming. Next week we'll kind of switch back to a little bit more discussion-y based stuff. And then the week after that, I think, is the week of 4-day, and also when the photometry project is due. Still a ways away, but not as far away as you might think. Time is weird. Before we get into this too far, I wanted to just really briefly show you galactic coordinates. Almost no one uses these, so I don't want this to be something that you spend too much time on. If you're doing Milky Way science, it might come up, but otherwise it almost never does. So it's an alternative method to tracking positions on the sky from RA and DEC. Most extragalactic astronomers use right ascension and declination, so these almost never get used. But the idea is you have a longitude and a latitude. Longitude is straight out from the sun looking to the galactic center is a longitude of 0, and then as you rotate around you go up to directly away from the galactic center would be 180, and you get 90 and negative 90 on either side. So sorry, I have to remind myself, and we're moving in the opposite direction of the galactic rotation. And then galactic latitude, just 90 is directly out of the plane of the galaxy towards the North Galactic Pole. Negative 90 is out of the galaxy to the South Galactic Pole. And I think it's opposite right-hand rule. You go with the rotation. I don't know. For the most part, like I said, no one uses these, but it's important to know that they're there. The reason you might want to use them is if you are working with looking into the disk of the galaxy, and that's the easiest way to do it. But it's, yeah, they're kind of a mess, and converting between RA and DEC and galactic coordinates requires a lot of trig, and I can never remember the formulas, so I usually just ask my computer to do it. But it's very rare that you have to. So just so you've seen those and you know that they are there, galactic latitude and longitude are another way of tracking positions on the sky. So today what we're going to focus on is more kind of the galactic ecosystem, looking at some of the different habitats where stars live, where they are born, where they evolve, and where they die. And thinking about just what it's made up of, how it travels through the interstellar medium, so the gas and dust within our galaxy. I will do my best to always call it the interstellar medium for our first few weeks, but we'll probably also refer to it as the ISM, because that is how what I'm used to. Astronomers, if you haven't looked up the bad astronomy acronyms webpage, we're terrible. We're the absolute worst. Yeah, Gandalf and Sauron are really bad. There's also Batman is something, I can never remember what. But anyways, that's not for today. So we'll talk about kind of the different, today we're going to be focusing on those different environments or habitats within our galaxy, and just thinking about the different properties of those and what's going on in those different areas. So we're also going to focus on spiral galaxies. So I'd say that now, because ellipticals don't have structure. So that's one of the big things. They're just kind of blobs. They do have nuclei, but that's it. The rest of them are just kind of fuzzy. There's no really organized movement in ellipticals. So when we talk about galaxy structure, we're going to focus on spirals because they are more interesting. Spiral structure is kind of made up of 3 components, the disk, the bulge, and the halo. Each of those components are made up of different types of stars and gas, so we'll kind of break them down further, but you can learn different things by studying different parts of the galaxy, looking in different areas. But this cartoon, I don't know where I am, here just shows you kind of the basic structure. We've got our nucleus, which is this big nucleus or bulge in the center, disk, and then a halo that it all resides in. So starting with the biggest part, we're going to start with the halo. Halo is also made up of 3 components. So halo is made up of stars, gas, and dark matter. The stars are going to be older, so it's mostly population 1 stars, those oldest stars, really low metallicity stars. A lot of them are in globular clusters. There's also some stellar streams, which we will talk about in the next slide. The halo is what we call dynamically hot, which means there's lots of random motion and not very much kind of circular orbital motion, or not orbital, but like motion of stars together. So everything's moving just kind of randomly. We're orbiting our galaxy, but just there's no disk, there's no overall motion together for most of these stars. The Milky Way's halo is about 130,000 light years across, so it's very large. What we've noticed, the image here is an image of Andromeda's halo, if we could see in the ultraviolet. So very bigger than the galaxy itself, very much bigger. Andromeda and Milky Way are going to slam together eventually, which I'm sure is something y'all have stumbled across in your time. But what's really crazy, something I read while kind of prepping for this, is that we think the halos of Milky Way and Andromeda are actually already starting to slam into each other just because they are so much bigger. So as we get more information about the sizes of these halos, we learn that they are actually already starting to overlap. That image too, that's looking at the coronal gas in the Andromeda galaxy's halo. So coronal gas is kind of similar. Its name is taken from the corona of the sun, where you get that exponential temperature increase in the outer layers of the sun. Similarly, the coronal gas in galaxies is extremely hot. So not very dense, but extremely hot. So 10 to the 4 to 10 to the 5 Kelvin. And they think we don't know 100% where it comes from, but we think it's mostly from supernova ejecta. So as supernova explode and they blow out into they push some of their material out of the disk of the galaxy, and it has a lot of energy, is often highly ionized, and we get this really hot coronal gas in the dark matter halo, or in the halo of a galaxy, sorry. Almost choked on like my own spit there. Sorry, that was gross. TMI, sorry. The other part of the halo is, of course, the dark matter. We will talk more about dark matter when we look at rotations and spectra, but we do know that every galaxy resides inside of a dark matter halo. So we can't see it, but we can measure it looking at dynamics of gas and stars and everything else within a galaxy. So we know it's there, but it does not interact with light, so therefore it's dark. The other thing that happens in that we can do with the other thing that we see in halos are stellar streams. So we can do some galactic archaeology with these stellar streams to try to determine the history of a galaxy. This is I don't remember what galaxy this is, but what we can see, we can see these kind of paths, these stellar streams of dwarf galaxies that are getting eaten by this larger galaxy. So we call it galactic cannibalism, when a big galaxy eats a little galaxy. It is actually called galactic cannibalism. But we can see it's being kind of pulled, this little galaxy is being pulled apart as it rotates around this bigger galaxy. And we can use those stellar streams to figure out the history of a galaxy, how many times it has merged, how many times it has eaten a smaller galaxy. A lot of times these stellar streams are made up of older stars, but they're often a single age as well, which is cool. So you can kind of use that to look for stars that are all the same age and seem to be traveling with similar velocities, and that'll give us an idea for the Milky Way, where we might have a stellar stream. So this is kind of an image, I think this is SDSS. I'm not actually sure, I should have looked that up, sorry. But we can take maps of the stars in our own sky. This might actually be part of pandas. I think that's right. Okay, I will check. Sorry. We can get maps of the stars in our own sky and look at how they're moving to map the stellar streams within the Milky Way. So there's a few big ones. The Sagittarius stream is a really big one that people study, where there was a small galaxy, the Sagittarius dwarf galaxy, that was ripped apart by the Milky Way. And we can still see kind of the history of how, where these clumps of stars are that are moving around the Milky Way. There are a few other streams, the Palomar 5, and then these Orphan and GD1 streams. We're still trying to study them and understand the history of the Milky Way by piecing together what happened as these dwarf galaxies were pulled apart by the larger Milky Way galaxy. So that's pretty much the halo. We have our population 1 stars both in globular clusters and in stellar streams. Hot diffuse gas that's often called coronal gas, and then dark matter. Any questions about halos before we get into some disks? Okay. So the disk, we're going to break up into 2 components, kind of 3 components, but the thin disk and the thick disk are the main 2 components we look at. There's also a gas disk, which is part of the thin disk, but it's even thinner than the thin disk. So the thin disk is where most of our stars are. So 95% of all stars in disk galaxies are in the thin disk. Every young star you're going to see is going to be in the thin disk because none of them live long enough to end up in the thick disk. They form in the thin disk where the gas is and never live long enough to get booted out into the thick disk. The thin disk has a scale height of about 300 parsecs, and scale heights are kind of the exponential, the factor by which the density of stars has fallen by a factor of E. So it's the distance at which the density of stars has fallen by a factor of E. Sorry, I should have checked that. Checked how I said that first. So it's this H in this equation here. So sometimes when we talk about atmospheres as well, you might have heard the word scale height in a planetary class. It's similar, except now instead of density of particles, we're talking about density of stars. So very, very thin. Especially compared to the size of the Milky Way. So I gave myself a little note here. The Milky Way is about 100 times wider than its own height. So if we shrank the Milky Way down to the size of a pancake with maybe a 10 centimeter radius, because I like big 10 centimeters, so like a fairly large pancake. I like pancakes. It would only have a thickness of about 4 millimeters. So very, very thin. We kind of think of galaxies like frisbees, but they're more like even thinner than crepes or something. Like they're very, compared to how wide they are very, very, very thin. The thick disk then is kind of outside of the thin disk, slightly thicker, has a scale height of 1 kiloparsec compared to that 300 parsecs, so slightly thicker. Stars that it's mostly older stars. I misspelled some there, whoops. But some of them are older stars that have been kinematically kicked out of the thin disk. So through gravitational interactions with other stars, you might get a little extra vertical motion that could push you into the thick disk. You also have some stars that are pulled in from those streams. So if you have merging galaxies, you can get some of those. If you've been merging for long enough, your stars will eventually collapse onto your thick disk. Because that's where these stars are coming from, they're always going to be older stars. So yellower stars, there are going to be no star formation happening in this thick disk because there's no gas, there's nothing to form stars from. Like I said, there's kind of a third component, the gas disk, which is thinner than the thin disk. It has a scale height of about 150 parsecs, but this also varies a lot with radius, depending on where you are within your disk. the reason it's so thin is because there's a lot of collisions where we lose that vertical angular momentum. So if you have a bunch of gas particles all traveling around, bumping into each other, there's just going to be a good likelihood that over time they will lose their vertical motion and end up all kind of traveling in the same disk, in the same rotational motion. Since they're all already orbiting together in the same direction, it's just more likely that you'll bump into something traveling the opposite direction and lose your vertical momentum over time. We'll talk more about what that gas disk is made of next class and like get into just the different phases of gas, or phases. They're not really phases because it's all gas, but just the different phases of the ISM next week. So we'll talk more about the gas and galaxies soon. Inside the disk, there are of course also the spiral arms. So by measuring the motion of gas and dust and stars in our galaxy, we've been able to kind of get this image of the different arms inside the Milky Way. So this is our basic idea of the map. There's the Perseus arm, and then these two Carina Sagittarius and Scutum Centaurus arms, as well as potentially a Norma arm and a few smaller arms that we are inside the Milky Way, so it's very hard to map the arms within our own galaxy. Spiral arms are also pretty funky to model and understand, so I'm going to do my best with what I know, but just know that this is a whole area of research, and modeling spiral arms is something that is still being understood, that we don't completely understand at this point in time. So the basic idea with spiral arms, though, is that in theory you should kind of get spiral arms over time if you have a disk of loose material all orbiting together because of differential rotation. So stars near the center of your galaxy take less time to orbit, stars further out take longer to orbit, and we start getting these kind of spiral patterns over time. The problem with this differential rotation theory is that you wind too much and you should have way more spiral arms than you actually end up having. So this is one theory about how we form spiral arms, but it doesn't quite work out in terms of observations, because we don't see this kind of mess. We see stuff that looks very much more like this. So with just one or two spiral arms that are usually pretty loosely bound. So we need something else to maintain spiral structure, not just differential rotation. And that's likely that the spiral arms aren't actually the motion of the stars within the disk. They're instead density waves. So a lot of times we think about this, Andrea might have talked about it in terms of kind of a traffic jam, where you move in and out of the traffic jam. So I always think, this probably isn't super helpful, but in Oregon, when you drive from Portland south towards Eugene, you go by kind of a strip mall, and every time you drive by that strip mall, the traffic increases because everyone's going to the outlet mall to get cheap clothing. So there's kind of a density wave around the outlet mall, and you move through it as you drive through traffic. So you're in a non-dense region, and then you're in a spiral arm dense region, and then you move out as you go through traffic. So we kind of think the same thing is happening. The spiral arms are like traffic jams within the galaxy that the stars move through. So spiral arms are rotating at a different rate for the most part than the stars and gas in a galaxy. We see spiral arms, especially looking in blue, because as clouds of gas and dust travel into the denser spiral wave, you get collapse, and that's when we form stars. And the young stars, the big massive stars, the blue stars, sorry, will only live for the amount of time it takes for them to travel across the arm. So they'll be short-lived enough that the entire time that that gas cloud is traveling through the arm is their entire lifespan. The older stars will then travel through the traffic jam arm and move out eventually, so we can see yellow stars in the disk and bluer stars in the arm. The other idea is that with this density wave, the reason we have a density wave that stays constant over time is because stars are kind of pulled in and held back as they move out through gravity. So as they get to the slightly denser area, they're pulled a little faster. They start to orbit slightly faster. And as they leave, they start to orbit slightly slower. So they're still traveling with their circular velocity kind of set by not quite Keplerian motion because they're in the dark matter halo, but set by general relativity, essentially gravity. They're still moving around the disk at that specified, at the rate they should for being inside of a gravitational blob, kind of circular mass, distributed mass. This is where the classical mechanics gets kind of tricky for me. Sorry, I have to keep in mind. So they travel slightly faster as they approach the density of the arm, and they travel slightly slower as they move out because they're approaching a gravity mass over density. As they move in, gravity pulls them forward, and they're leaving a mass over density as they go, so gravity pulls them slightly backwards. But they're still moving in their kind of orbital motion path around the galaxy caused by most of the mass, which is in that dark matter halo. This still doesn't answer a lot of questions about spiral waves, like what forms them in the first place and how they are maintained, but it does give us a bit of a way of preventing the winding problem and understanding spiral arms, how at least why they kind of are there and why they look the way they do. So maybe you start with some winding and then somehow, because of gravitational changes within the disk, we end up with stable-ish arms, but we really aren't 100% sure. And this is a whole area of research still. So if this is something you're interested in, there's a lot that we could still learn here. And just as another way of showing this, this was from a paper that was looking at how we could try to prove density wave theory by looking at spiral arms in different wavelengths and looking for older stars and younger stars being in different areas. So this just shows kind of a model of spiral arms and what they were looking for. So where they thought bluer stars should be pretty close to the gaseous disk, the arms, whereas redder stars were going to be kind of either in front of it or behind it, depending on where you are within the bulge or within the disk of the galaxy. The green line here is the co-rotation radius. So this is a point within any galaxy. It's usually pretty close to the bulge or nucleus of a disk galaxy, where the spiral arms and the motion of the stars are orbiting at the same rate. So there is going to be a point, because the arms are rotating and the stars are rotating, there has to be a point where they are equal. It's usually fairly close in towards the center, and that's the co-rotation radius. But this group was looking to try to test the density wave model by looking for where different stars were, where star formation was occurring. And what they found was that it seems to be right that we are seeing density waves and not actual winding arms. So that's kind of my overview of spiral arms. It's a little rough, partially because we don't know a lot about spiral arms and how they form and how they don't just dissipate over time, and partially because there's a lot of orbital mechanics and gravitational general relativity stuff that you need to understand to do this that I do not know. So that's just kind of where I am. These are just some of the basics about spiral arms. Does anyone have questions before we push forward? So the last thing I'm going to try to do my best to talk about is bars within galaxies. So about 2/3 of spiral galaxies seem to have some form of bar. The Milky Way also has a bar. Based on models of how orbital rotation works, it does kind of make sense for bars to form, because once you have a density perturbation somewhere, gravitationally, what you end up getting is a bar. So a density perturbation will cause, there'll be more mass in one area, so all the stars will be kind of pulled towards that one mass as they also rotate around. And as that happens, over time, you eventually form a bar. So any disk with any density perturbation should form a bar. So kind of the biggest question is, okay, why, instead of why do 2/3 of spirals have bars, the question should be, why do only 2/3 of spirals have bars? And the answer to that is essentially dark matter halos. So if you have a uniform enough dark matter halo that your galaxy is within, that will kind of override the fact that there are changes in density from the spiral arms, or from in the stars and the gas in the disk, and it'll just kind of smooth everything out, smooth the rotation out. So the fact that not all disk galaxies have bars was some of the first evidence that there must be some sort of massive halo surrounding disk galaxies. So before we had Vera Rubin's measurement of the rotation of galaxies, we had this idea that the lack of bars within galaxies suggests that there must be some form of massive halo around galaxies. Even with that, now that we can model dark matter halos, we still don't completely know how they absorb the amount of angular momentum that is present within disk galaxies from density perturbations that cause these bars. So we don't really understand, despite the fact dark matter halos are there, we still don't really understand why not all disk galaxies have bars. Kind of a weird thing. The other, did I freeze it all? I got a message saying my internet was unstable. Okay, hopefully we're all right. The other thing I wanted to point out here, I don't want this to be something you worry about too much, but there is a property called the turmeric Q that you'll hear about on occasion when we talk about disk galaxy rotation. And it's a stability criteria for measuring for the motion within disks. It's equal to this funky thing down here. So it's the speed of sound times the epicyclic frequency, denoted by kappa, divided by g times pi times the surface density of gas. So the epicyclic frequency is just kind of a measure of the angular momentum within the galaxy. That's as far as I want to get into it. There's another way of measuring, this is for gas. You can also do it for stars. It becomes a little different where you look at kind of the, standard deviation of the velocity. So you look at how the stars are moving, again, multiply it by the epicyclic frequency and then divide it by this factor, 3.36 times the universal gravitational constant times the surface density of stars. The big important thing is if your turmeric Q is above 1, you are stable. That's the main thing I want you to talk about this, take away from this discussion. So turmeric Q is a value that gets thrown around on occasion. The important thing is that if it is greater than 1, your disk is stable over time. If it is less than 1, your disk should collapse into something, to a blob, probably, over time. So, or at least lose structure. Another thing about bars that is kind of interesting is that we see over time more and more galaxies seem to have bars. So this is a graph of the fraction of barred disk galaxies versus look-back time or redshift. And so what we can see is that over time, the fraction of galaxies that they're looking at that did have a bar is increasing. So this might tell us something about how, as galaxies evolve, one of the things they do is form bars. Maybe. I think this is still kind of how we're forming bars and why we're forming bars and why not everything has a bar. We're not quite sure, but maybe it is something that is changing with time, and maybe that tells us a little bit more about why we might form a bar as we move through the history of the universe. So the Milky Way does have a bar as well, we're fairly certain. So we are in that 2/3 of disk galaxies with bars, and we can measure that by looking at the motion of gas in the plane of the Milky Way, and we can see that it's shaped in a way that means there must be a bar. Any bar thoughts or questions? Okay. So the last part of a galaxy is the bulge or the nucleus of the galaxy. You'll hear it called both things, so that's why I'm putting both these words out there the same, just two different ways to referring to the kind of big blobby thing in the center that is often very yellow. There is continuous star formation in bulges, but because there's been so much star formation, they're dominated by older stars, so they often look yellower. So there are still young stars in the bulge, but there are so many old stars there that they often look yellow. The bulge of the Milky Way is about 10,000 light years across, and it has a luminosity of about 5 × 10⁹ solar luminosities and a mass of about 2 × 10⁻10 solar masses. So very massive. It's of course where Sagittarius A star is, that supermassive black hole at the center of our galaxy, which we talked about earlier. And when we get to AGNs, we will talk more about supermassive black holes. So we'll get to that more later. Bulges or nucleuses can come in a lot of different shapes and sizes. So here we can see this is a galaxy where we can see a very prominent bulge, whereas this galaxy has a very small bulge. Why they are this way, again, this is kind of a galaxy dynamics thing. I'm not sure that there's a solid answer at this point, but most spiral galaxies have some form of bulge and nucleus. A lot of the different color structures that we see over time have to do with star formation rates. So anywhere where there's gas and dust, you will get more star formation rates. And as you either run out of gas to make stars or get a continuous source of gas, if you're maybe out more in the disk, we will either see that run out or continue over time. So that kind of has to do with it. And then the actual structure are formed through gravitational pulls from density perturbations throughout. So that is my kind of vague, doing my best to understand the orbital mechanics of galaxies and just the structures within them. I think there's a lot we don't know, and there's a lot of, if you get into this, there's a lot of pretty intense modeling using spherical harmonics and stuff, but essentially this is, instead of a 8 or 9 body problem like our solar system, this is a billion body problem where we're also inside of a dark matter halo. So completely understanding all the motions of everything within a galaxy gets to be pretty complicated pretty quickly. And that's why we use computer programs to do it instead of trying to do it by hand. And I wanted to end on this image before we get into our activity for today, because this is our Milky Way's disk put across the sky. You can see the large Magellanic Cloud down here, kind of shining. But one thing to note is that our bulge is kind of shaped like a peanut-ish, but it's very boxy. And that's one of the ways that we know that we are in a barred disk galaxy instead of just a disk galaxy. So the boxy structure of this bulge is one of the things that suggests that we are in a barred disk galaxy, along with the motions of the gas. So for large structure within a galaxy, just to wrap up one more time, sorry, I'm not great at ending lectures. But we have our halo that's made up of coronal gas, hot gas, old stars, and dark matter. We then have our disk, which is made up of the three parts: the thin disk, the thick disk, and the gas disk. Thin disk is most stars, thick disk is a few older stars, and then the gas disk is most of the gas in the galaxy. Finally, there's our nucleus in the center that has our supermassive black hole, along with a lot of old stars and some ongoing star formation. So that's kind of the basic structure of spiral galaxies. Now what I want you all to do is to try to see one way that we can kind of test this out and measure structure in a simplified way by looking at surface brightness with radius. So that is our day 7 activity. I've given you images of 2 galaxies, an elliptical galaxy and a spiral galaxy. And we're going to try to plot surface brightness with radius. So this is going to look similar to what you did last class, except now we're going to do it many times. That sounds scary. It's going to be okay. So I'm just going to try, let me go to one that doesn't have the solutions. I'm going to walk through what we do. And this is again, if you don't have photutils downloaded, but they should look pretty similar. So the first thing that you do in this code is you load up all of the different programs that we will use. They should look semi-familiar at this point. Mostly it's stuff from AstroPy, as well as some plotting code from Matplotlib and just NumPy, which has mathematical formulas and some constants that are important. So pi is one of the things in NumPy. And then this is my janky-ish aperture photometry code. And then we load our data from the 2 galaxies. So our spiral galaxy and our elliptical galaxy. I tried to be consistent. I tried to make it obvious, but you guys are seeing how my brain works when I do these. So my spiral galaxy I called S because the name was long. So S indicates that we're working with the spiral. And then I think I actually used the elliptical name when I was talking about the elliptical. So this just loads all that data. Again, we're working with the FITS file, so we have to tell it which extension we want to use, but we're always going to use the 0th or first extension. Then just for fun, I plotted them so we can see what they look like. NGC 628 is a pretty spiral, and then M89 is a pretty typical elliptical galaxy. I'm going to give you the RA and deck, which will be important. I do it then for our plot for our elliptical galaxy. So we make a star coordinate using AstroPy's star coordinate function centered on the center of our elliptical galaxy. And I'm just telling it we're working in degrees and we're in the J2000 RA deck. So this is just, we'll always be working in this frame, so don't worry too much about changing that. And then I tell AstroPy to go into the header of this file and pull out the information, the World Coordinate Systems information, or the WCS information for this file that just tells us which pixel corresponds to what location in the sky. So that's what this is giving us. And then we can convert our location on the sky into a pixel location. So that's what this line of code is doing. It's saying, tell me the pixel coordinates that correspond to this RA and DEC in my M89 image. Then just to remember, just as a quick step, we find the brightness in arbitrary units at this moment of the center of this galaxy. So RA and DEC, or so X pixel, Y pixel, sorry, radius in pixels, and then the data we want to be working with. So we loaded that earlier, and then I just print it. So that's similar to what you did last week. We're just going to do that for a bunch of different radii. So I've made just kind of an array, or I guess this is a list actually, they're similar, of different steps out in radius. I've given you the conversion between arc seconds and pixels for both of these images. They're the same. And then I said, let's convert all of these values from arc second radius into pixel radius. So I think the people working with utils, you won't see this because you don't need to see this. But this is just dividing a radius in arc seconds by a conversion from arc seconds to pixels to get a radius in pixels. Then I use a for loop to get to do aperture photometry for each of those different radii. So I'm also plotting circles. Whether or not you do that step is up to you, but it's helpful to kind of see what we're looking at. So this first two are just to get circles of different radius to plot using matplotlib. And then I extract a flux for every one of my radii. So I'm saying for every value within this list, I want you to run this code. So for all values in this list, perform this code, where X is going to be that radius. So I eventually create an array called flux, where I've added in all of those new fluxes for the different sized apertures. So here's our elliptical galaxy. All of the apertures I used are these blue circles, cyan circles, as we step out in radius, centered on the center of my galaxy. Yeah, and we can see that my flux is what I called my array that just has all of the flux values, where I'm saying add up all the fluxes within this circle. So then to turn that from a flux into a surface brightness, I'm not going to worry about conversion factors this time because we're just interested in how things change with radius, so we don't have to worry about converting units. We're just looking for shapes, which is awesome. So we get to take out all those steps. We just need to find the area of every one of my apertures. So we can divide our flux by this area and plot using a scatter plot. We can plot radius. So radius was the radius of our aperture. So that's just the distance out we're going in the galaxy, divided versus the flux per area within that aperture. And we can see how surface brightness kind of changes with distance out in the galaxy. So that's what I did. Your task is to now repeat that for the spiral galaxy, for NGC 628, so we can see how spiral galaxies might look different. Remember, once you download your notebooks, that you will have to rerun all of my code, even though the graphs are there, in order to load the data. So a little note, and I'm gonna go ahead and put you in some breakout rooms so you guys can potentially talk together, but also feel free to grab me if you have questions. The room should be open, and we'll work on this for the rest of class. Our spiral galaxy is going to look a little different. It's going to kind of flatten out in a different way. So this is just a way that we can sort of measure kind of a bulge and a disk in a spiral galaxy and how that'll look different. I wanted to point out also that in order to make this a little less painful, I skipped quite a few steps. I did not subtract a background, so these all include backgrounds. The other thing I didn't do is I just kind of I kept, a lot of times if you're plotting surface brightness with radius, you want to do it in rings instead of in just bigger and bigger apertures. So you want to make your donuts. The way you would do that is you would subtract the previous value. So that's another thing to like think about. So you'd say you'd add up all inside and subtract that from your one, and then you get a ring instead of a circle. You'd get a donut, and that would actually be the surface brightness for that radius instead of the surface brightness all enclosed. So a lot of times we would do that instead of this, but we get kind of the right shape. You can kind of see from the top of this notebook how you can measure exponential disks using this method and see the differences between a bulge and an exponential disk, and also how ellipticals and spirals might look a little different in these surface brightness profiles. So I just wanted to point out those few things. The solutions are in our files, and I will add them to this